What's going on, guys? In this video we are going to see an example of the instrumentation amplifier. For an instrumentation amplifier, the V output voltage expressed like this: R2 over R1 times 1 plus 2R3 divided by R4 times V2 minus V1. In this particular video we are going to see how to derive this equation. Okay, here you can see these two op amplifiers are connected to this one, so the voltage input is going to be from whatever the voltage output from this one. That's going to be the voltage input for the third amplifier. Now first we are going to calculate the voltage output for these two amplifiers. For these two, you can see the input voltage is connected to the positive terminal, so this is a non-inverting op amplifier. For a non-inverting op amplifier, we use this equation to calculate V output voltage. So for the first one, VO1, that's going to be equivalent to 1 plus feedback resistance. In our case, the feedback resistance for this one is equal to R3. Okay, so this is going to be R3 divided by R4 times the voltage input, that is V1. Okay, so this is VO1. Then we are going to calculate VO2. VO2 also same thing, that is the input voltage is connected to the positive terminal, so this is also non-inverting op amplifier, so the expression is going to be similar to this. So we are going to have 1 plus R3 over R4 times V2, because R3 is the feedback resistance, R4 times the voltage input, that is V2. So we have derived these two equations, and also we can create equations for this current. And we know that for an ideal op amplifier, there's no current flowing in or out of this positive negative terminal, so the current is 0 right here. So whatever the current going through this one should be equal to I, like I is everywhere. This is in series, so I must be equal everywhere, right? So first we can create the I equation based on this voltage, and the resistance in between. So first we can say, since the current is flowing in this direction, that's going to be VO1 minus VO2 divided by the resistance in between, that's going to be 2R3 plus R4, because all of them are in series. So 2R3 plus R4, and that is it for this one. And also based on these two nodes, we can create another equation for the same I. We can say I is equivalent to VA minus VB divided by R4, and you can see this VA voltage is right here, and this is going to be the same voltage in the negative terminal, right? So and also we know that for an ideal op amplifier, whatever the voltage in the positive terminal is equal to voltage in the negative terminal. Therefore we know that voltage in the positive terminal is equal to V1, therefore voltage in the negative terminal also V1, and therefore VA is equal to V1, because VA is the voltage across negative terminal, that is equal to V1. So instead of VA minus VB, we can replace that one with V1, and for VB it's the same thing. Voltage across the positive terminal is equal to voltage across the negative terminal, so V2 is also in the V minus, like negative terminal, and negative terminal voltage is VB, so we can say VB is equal to V2. So this is V1 minus V2 divided by the resistance in between. Now since the currents are equal, because no matter wherever you pick, the current is going to be same everywhere, right? So this I are same, right? We are looking at the series current, so we can equate these two equations. Okay, let's say VO1 minus VO2 divided by 2R3 plus R4 is equal to V1 minus V2 divided by R4. So now we have derived the equation. Now here we are going to bring the equation in terms of VO1 minus VO2. VO1 minus VO2 is going to be multiplication of this one with this one. So we are going to have V1 minus V2 over R4 times 2R3 plus R4 divided by 2R3 plus R4. That's it, right? That's it. And also we can move this R4 with this one. In that way we can have the resistance all together. So let's bring this R4 to this one. We can put it in the denominator, so all the resistance are together. Okay, so now we have derived the equation in terms of VO1 minus VO2, and here you can see we can cancel this R4 and we can get another better expression. Now let's get rid of this part. let's get rid of this part and continue here. Okay, so I'm going to continue on top. Okay, here we have this one, therefore we can say VO1 minus VO2 is equal to V1 minus V2 times R4 over R4, that's 1. So we can say 1 plus 2R3 divided by R4. So this is another way to write the same equation. Now we need V output voltage, that's our main purpose. Now we are going to see how to derive the equation for V output. Now we are going to express the V output in terms of feedback resistance. For this one, this is going to be V output voltage is going to be feedback resistance over the input resistance, that's R1, multiplied by the voltage difference, that's going to be VO2 minus VO1. Okay, VO2 minus VO1 minus VO1. Now instead of VO2 minus VO1, we can bring this equation VO1 minus VO2, but here VO2 minus VO1, right? All we have to do is just flip the V2 to the front and V minus to the other side. In that way, it's similar to multiplied by -1, right? So I'm going to replace this VO2 minus VO1 with the opposite of this sign. Okay, that's going to look like R2 over R1 times, we are going to have this 1 plus 2R3 over R4, and then we are going to multiply this one with V2 minus V1. Okay, V2 minus V1, and that's it. Now let's see whether this is our final expression, R2 over R1 plus times 1 plus 2R3 over R4, V2 minus V1. Okay, so this is, we derived the final equation. So this is our final equation. Okay, and also we can express this one in a better way, like, let's get rid of this part. For example, let's say we have, and we can call this one as gain. Okay, this is gain. And also, like, if R2 is equal to R1, we can express this equation as VO is equal to 1 plus, because this ratio is going to be 1 plus 2R3 over R4 times V2 minus V1, and this part is gain. Gain is, we call gain A, and that is equal to 1 plus 2R3 over R4. In that way, we can express this one as VO is equal to A times V2 minus V1. Okay, so this is going to be our final expression. I hope this helps. Thanks for watching.